In the previous lecture, we were interested in stability properties in the set of CR maps between two differentiable manifolds, stability properties with respect to the strong topology. Here, our point of view is going to be a little bit different. Suppose, for instance, that we are considering two C-infinity manifolds and that we have a CR map between them. Our goal in this lecture is approximating the CR map by C-infinity maps, or in other words, showing that the set of C-infinity maps is dense in the set of CR maps. In that way, we are going to be able many times for many applications of replacing CR maps with C-infinity maps without any lack of generality. Okay, so consider two CS manifolds, M and N, and consider R, which is greater or equal than 0 and smaller than S. We want to approximate CR maps with CS maps in the set of CR maps from M to N. And the approximation is considered with respect to the strong topology, right? So let us introduce the main technique that we are going to use in order to approximate CR maps with C-infinity maps. So let's consider what it is called a convolution kernel, which is going to be a function from Rm to the non-negative real numbers, okay, such that it has compact support and that has an integral on Rm, something that is well defined because the function has compact support, that is equal to 1. Sure, in order to consider the integral, we have to require some level of regularity, but we are going to suppose that indeed theta is a C-infinity map. So we can consider that integral, and we are going to require, in order for theta to be a convolution kernel, that the integral is equal to 1. The minimum positive number delta, such that support of theta is contained in the closed ball of center 0 and radius delta, is called the support radius of theta, right? That support radius exists because the support of theta is a compact set. And we have this fundamental lemma that we used when we were studying partitions of unity. And it is that given positive real numbers, A and B, with A smaller than B, and some natural number n, there exists a C-infinity function, eta, from Rn to the closed interval whose extrema are 0 and 1, such that eta is equal to 1 if the modulus of x is less or equal than a, and eta is equal to 0 if the modulus of x is greater or equal than b. Okay, and what we have here is that if we replace the function eta with the integral, with the quotient of eta and its integral, the integral of course is a positive number because this is the integral of a non-negative function, but that is equal to 1 in the ball of center at the origin and radius a, so the integral is at least going to be the volume of such ball. And this function over here is still C-infinity. The values of such function are still non-negative, and the integral now is equal to 1. So this is an example of a convolution kernel. And the support of theta is contained in the closed ball of center 0 and radius b. So the support radius of theta is less or equal than b. So we can, in this way, obtain convolution kernels whose support radius is arbitrarily small, right? Very good. Okay, this is the result that we just announced, is that given a natural number and some positive real number epsilon, there exists a C-infinity convolution kernel. Here, of course, there's something missing. There exists a C-infinity convolution kernel in Rm whose support radius is less than epsilon. Okay, this is something that we already saw we can do. Okay, now we want to use these convolution kernels to consider smoothings of the map F, right? So consider a map F from U, which is an open subset of Rm to Rn. And let us consider a convolution kernel theta support radius is less or equal than that. We are going to define the convolution of theta and f, this theta star f, which is going to be defined in U delta, where U delta is the set of points x in U, such that the closed ball of center at x and radius delta is contained in U, okay? And it's going to be defined by this formula over here, right? So is this definition actually a good definition? It makes sense? The answer is yes, because if we consider a point x in U delta, okay, what we have is that if y is a point in the ball of center at the origin, the closed ball of center at the origin and radius delta, then in particular x minus y belongs to the ball, the closed ball of center at x and radius delta, and such a closed ball is contained in U. Okay? And besides that, the support, so in particular, the value of f in x minus y is well defined, because x minus y in such a case belongs to U, is in the domain of definition of the map F. Now we have that the support of theta is contained in the closed ball of center at the origin and radius delta. And so that means that if we consider the map that goes from y to f of x minus y times theta of y, this map is actually a map that is well defined everywhere, because when theta is equal to 0, we just define this map as 0, and when theta is different than 0, this is well defined, that if theta of y is different than 0, x minus y belongs to U, right? So this is a continuous map that it is well defined in Rm, and whose support is actually compact because the support of theta is compact. So we can consider this integral for every x that belongs to U delta. Okay, so the definition makes sense, and this convolution is defined in this set U delta, which is slightly smaller than U. It's not the whole U, but it's a little bit small, right? Okay, we can consider another formula for actually the convolution. because we can use the theorem of change of variables for integrals. In particular, if we consider, for instance, the change of variables y equal x minus y hat, what we have is that this integral over here is going to be the integral in Rm of f of x minus y, that x minus y is y hat, times theta applied to x minus y hat. And now we have to consider the modulus of the determinant of the Jacobian matrix. But the determinant of the Jacobian matrix is going to be 1 or minus 1, and the modulus is going to be 1. So we have this. So that's the reason that actually makes this formula work. And this formula is, in some sense, a little bit better than the formula we used to define the convolution initially. And why is that? Because when you consider this map over here, okay, if you consider the first expression, it's just a continuous map. But we cannot say, for instance, that it's C infinity in the variable x, because it's not going to be C infinity in the x variable, because f is not C infinity, it's just a continuous function, so that does not make any sense. But if we consider the second expression, since theta is C infinity, this function over here is continuous in both variables, x and y. It's a continuous variable, it's a continuous function of R to m, and it is C infinity with respect to x, because theta is C infinity. And that's going to be something that is going to be plenty useful, and one of the reasons because this trick, the convolution, actually is works to smooth differentiable maps, right? So this is actually the second formula, and we want to see that the convolution is a smoothing operator, so that you consider a continuous map as an input, and this operator, the convolution, gives you a C infinity map as an output. So indeed, what we are going to have here is a C0 map from from U to Rn, and the convolution is a map from U delta to Rn. And our goal is right now showing that this map is indeed C infinity. Okay, let's see why is that true. We can actually consider the derivative of the convolution with respect to the variable xi. What we want is differentiating under the integral sign. Okay, but in order to do that, what we have to check out is that this function over here is continuous, which it is, because theta is C infinity. So we can differentiate under the integral sign. And in particular, this gives us an expression for the derivative of the convolution with respect to xi. Now, we can differentiate multiple times with respect to the different variables, okay? And in Rm, and by using a completely analogous argument, we have that this derivative over here, the derivative with respect to x1 I one time, x2i two times, and so on till xm I m times is indeed the convolution of f and the derivative of theta, the analogous derivative of theta, right? And again, we are using several times. Indeed, here, the number of times is the sum of the I sub j's. We are using finitely many times the theorem that allows to differentiate under the integral sign. Okay, and so we get this formula. But now, since all the derivatives of all orders of the convolution exist, that means in particular that the convolution is infinity. Okay, so we get in this way that the convolution provides a C-infinity map. Okay, so the first part of our program showing that the convolution is smooth is already working. But obviously we need more because we can associate to a function a smooth function. We associate to the function 0, for instance, and that's okay. And for a map, we associate to this map the constant map, and yeah, it's always going to be smooth. We need to show that the convolution is close to f somehow. And let us explain now how. Okay, well, first of all, as we already said, the convolution of theta and f is C infinity in its domain of definition, which is U delta, right? Now, let us see that the convolution is an approximation operator. Suppose that f from U to Rn is a CR map, right? And now consider the convolution, okay? Let us consider now the first formula. So here dx enters as an argument of f and not as an argument of theta. We can consider the derivative with respect to one of the variables, for instance, x1. And again, since, for instance, since f is at least c1, when we consider the derivative with respect to one of the variables, the function that, or the map indeed, that we get here as a map of x and y is continuous. So again, we can use the theorem that allows to differentiate under the integral sign to obtain the derivative of the integral, right? Of course, we can keep doing that a finite number of times. Since f is CR, we can derive R times, okay? So we are going to have this equality, okay, as long as we are derivating at most R times. From that moment on, it's no longer true that these derivatives are continuous. Indeed, it's not clear that they exist. And so the result is no longer true if we are consider derivatives of order greater than R, right? But this is a very interesting result because it's saying essentially that the derivatives of order up to R of the convolution are obtained as a convolution of the convolution kernel and the derivatives of f. Okay. And why is that interesting? Because we are going to have that these derivatives here of order up to R, that's really important, converge uniformly to the corresponding derivatives of f in compact subsets of U. And what kind of convergence we are talking about? We are talking about uniform convergence when the support radius of theta converge to 0. right? For instance, let us consider this with C0, let's see that the convolution of theta and f converge uniformly to f in compact subsets of U, right? So if you have, K, which is a compact subset of U, right? Okay. What we have is that since K is compact and the map F is continuous, then it is uniformly continuous in the compact set. That means that given a positive epsilon, there exists a positive delta such that if x belongs to K and x minus y has norm smaller than delta, then the norm of f of x minus f of y is smaller than epsilon, right? What happens now if we consider a convolution kernel whose support radius is indeed smaller than delta? Okay, let's see that. So what happens is that if we consider the convolution of theta and f in a point x of K minus f of x, this is going to be the integral, the convolution is going to be the integral in Rm of f of x minus y theta y dy, and now minus f of x. But since the integral of theta is equal to 1, a condition that we didn't use yet, we have that this is the integral of fx theta y dy in Rm, right? Now you have to take into account that the support of theta is contained in the closed ball of center at the origin and radius delta. So this is the same as the integral in Rm, in that ball, in the closed ball of, let's see if I can, the closed ball of center at the origin radius delta of f of x minus y minus f of x times theta y dy, right? Okay, but but what happens here, we are considering a point x in K, okay, is that this is the integral in the ball, in the closed ball of center at the origin and radius delta of f of x minus y minus f of x times theta di. Okay, but what happens is that x belongs to the compact set and the distance between these 2 points is at most delta, and because of that the norm of this difference is at most epsilon. So what we are going to have is that since the norm of the integral is going to be less or equal than the integral of the norm, we have this thing over here. Right? And this is going to be less or equal than the integral in the closed ball of epsilon times theta, but the integral of theta is 1, so this is epsilon. And we proved that if the support radius is smaller than delta, then the difference between f and the convolution of theta and f at every point of the compact set is smaller or equal than epsilon, right? This is very interesting because you can apply it to this case. Since we have this formula and this function over here is continuous, okay, this convolution tends to this function uniformly in compact sets as long as the support radius of theta tends to 0. So if the support radius of theta tends to 0, then this derivative tends uniformly to this one in compact sets. As long, of course, that we are, as long as we are considering derivatives of order up to R, because beyond R, this formula is no longer true, and we cannot say we don't have the same property that the analog. Okay. So this is interesting because the derivatives of order up to R for the convolution approximate very well the derivatives of order up to R of f. So convolution because of our previous discussion is a perfect candidate for our program of approximating CR maps with CS maps. Indeed, we can approximate CR maps with C-infinity maps. And as a consequence of the previous discussion, we have this theorem. Let theta be a convolution kernel of support radius delta. Consider a continuous map F from U to Rn, where U is an open subset of Rn. The convolution, which is defined in U delta, has the following properties. The first one is that the convolution is a C-infinity map, okay? Besides that, for any derivative, we have that the derivative of the convolution of theta and f is the corresponding derivative of theta convolution with f. And this is the reason because this map over here is infinity. Besides that, if f is CR, we have that the convolution, the derivatives of order up to R of the convolution of theta and f are the convolution of theta and the corresponding derivative of f. Okay? And we saw that as a consequence, if f is a CR map, epsilon is a real positive number, and k is a compact subset of U, there exists some delta such that the derivatives of f and the convolution of theta and f of order up to R have a norm, this difference has norm smaller than epsilon for all x in k and all k between 0 and R if the support radius of theta is less than delta. So if we have f, k, and epsilon, we can find delta such that if the support radius of theta is less than delta, we have this property over here for every k between 0 and R and for every x in k. So the convolution provides good approximations of f. So We can use convolution to approach maps between open subsets of Euclidean spaces with C infinity maps defined in some open subsets of U. They're not very far away from being the whole U. And such that these C infinity maps approximate well the derivatives of the initial map up to order R in the neighborhood of compact sets, right? And we will see that the density of C infinity maps in the strong topology is a consequence of this trick, the use of convolutions in order to approximate our maps with C infinity maps, and partitions of unity that are almost always necessary when we want to globalize results. The result that we got actually is a result for maps between Euclidean spaces. So when we use local charts for a differentiable map, we are going to be able of obtaining a local expression that is going to be a differentiable map between open subsets of Euclidean spaces. But okay, we are the convolution is going to give us approximations in these local charts, but we want an approximation defined in the whole space. And so in order to paste these local approximations, we are going to need to use partitions of unity. We define the convolution between a convolution kernel and a continuous map between open subsets of Euclidean spaces. And in that way, we obtain an approximation of our initial continuous map with a C infinity map. This is an approximation essentially in the weak topology, but we want more than that. We want approximations in the strong topology, which is a harder problem because the level of approximation that we need in the strong topology varies along the manifold. And so convolution does not suffice to obtain approximations in the strong topology. We are going to require, besides convolutions, also another tool, basically a tool that we have already used several times, partitions of unity. And this topic, approximating C0 or CR functions with C infinity functions, is going to be the subject of our next lecture. Thank you for your attention.